The Earth has a secret ocean 400 miles down, and it's about to break loose. The flood that never touched water. The ground shook before the steam did. Not from rain or rivers, there were none. A caldera floor exhaled, then fractured, and a wall of ash ripped into the sky. People called it a surprise flood, but no water ever touched air. It moved inside rock, bound to crystals, squeezed by pressure, released as melt and gas. By the time the plume spread, flights were grounded and noon looked like dusk. The question nobody asked was the only one that mattered. If this much water can explode without ever being wet, how much more is still trapped below our feet? And what happens when the valves line up? The hidden reservoir we didn't see coming. Water inside Earth, but not as pools or veins. Water locked into minerals as hydroxyl, single hydrogen and oxygen atoms stitched into a lattice. To hear it the first time, it sounds wrong. Under the kind of pressure you feel 400 miles down, rock behaves like a sponge you can't see. It doesn't drip, it remembers. That layer is the Mantle transition zone, a shell from roughly 410 to 660 kilometers deep. It's where olivine, ordinary upper mantle olivine, reshapes into high-pressure forms with room for water. At the top sits wadsleyite, deeper in ringwoodite. These aren't obscure names to petrologists. They're the reason the phrase Earth's secret ocean won't go away. The first hard proof didn't come from a drill. It came from a diamond. In 2014, a blue-tinted fleck of ringwoodite trapped inside a Brazilian diamond revealed what lab experiments had promised for years. Deep mantle ringwoodite can hold substantial water. Not liquid, not ice. Hydroxyl, locked in the structure, on the order of 1 to 2 weight percent. That tiny inclusion, a time capsule of pressure and chemistry, confirmed that the transition zone isn't dry. It's hydrated in the most literal atomic sense. Wadsleyite, the phase just above, can store a similar fraction under the right conditions. Experiments show ranges around roughly 0.65 to 1.5% by weight, depending on temperature, composition, and oxygen conditions. Those numbers sound small until you scale them to a shell that wraps the planet. Even patchy hydration, nowhere near uniform, could add up to the equivalent of roughly one surface ocean. The phrase several oceans gets thrown around, but the caution is real. Capacity isn't the same as inventory, and inventory isn't the same everywhere. So how do we know where it's wet? Seismology started whispering the story first. Waves traveling through the transition zone slow down in places they shouldn't, and they attenuate, lose energy more than expected. That combination hints at higher temperature, a bit of melt, or fluids changing how rock relaxes as waves pass. Around 410 kilometers, where olivine shifts to wadsleyite, and near 660, where ringwoodite collapses into lower mantle phases that can't hold water. Seismologists see signatures that look like dehydration melting. Small pockets of partial melt created when water is expelled into rocks with lower melting points. It's not a fire hose, it's a thin film that changes everything. Electrical imaging adds a second voice. Magnetotellurics, MT, listens to natural electromagnetic fields and measures how easily the subsurface conducts electricity. Dry mantle is resistive. Add water in defects, add tiny fractions of melt, and conductivity rises. MT maps have begun to outline conductive pathways under arcs in hot regions, consistent with hydrous, partially molten domains tapping the transition zone. None of these methods measure water directly. They triangulate it through physics and are non-unique. Melt, sulfides, graphite, or hydrogen in defects can all raise conductivity. The picture they paint is modeled, not uniform. Reservoirs align with subduction corridors in places where plumes might pull material upward. What kept it hidden is simple. It was never free to see. The water is built into the rock, not filling cracks, not forming reservoirs that reflect seismic waves the way liquid would. Under pressure, minerals change shape and chemistry in ways that create sites for hydroxyl to bond. Think of it like a charge stored in a capacitor. Energy held quietly until the circuit changes and the charge moves. Subduction carries hydrated minerals down. The transition zone stores, upwelling spend. The human moment that flipped the conversation wasn't a dramatic field expedition, it was a lab microscope over a flawed gemstone. A geologist looking at a blue speck in an otherwise colorless diamond recognized ringwoodite, a phase that shouldn't exist at the surface unless it rode an elevator up from depth. Then came the analysis. The structure held hydroxyl. The implication landed hard. We didn't just suspect a hydrated transition zone. We had touched a shard of it. But proof is only a beginning. The questions that matter are about movement. How does water get
Delivered in the first place? When do those defects in crystal lattices let go and become melt that can climb? And why do some parts of the transition zone seem saturated while others are starved? The answers don't sit at the surface. They live in the deep water cycle, a long, slow loop that drags ocean water into the mantle, hides it in mineral sponges, and occasionally releases it in ways that rewrite landscapes and climates. To understand the stakes, you need to follow a drop that never becomes a drop. From rain at the surface to a hydrogen atom locked in ringwoodite and back again in ash and steam. The discovery in a diamond told us what is there. The planet's behavior tells us what it can do. Now we go back to the beginning, not of oceans, but of subduction, pressure, and the kind of chemistry that sets timers we rarely see until they go off. The deep water cycle that runs the planet. Start on a rain-soaked ridge above an ocean trench. That water won't stay water for long. It seeps into oceanic crust, reacts with hot rock, and builds minerals that carry H2O without looking wet. Serpentine in the mantle peridotite, lawsonite and chlorite in the altered crust. Every pore, every crack, every cooling fracture invites the ocean inward, and chemistry does the rest. By the time that slab reaches the trench, it isn't just rock, it's a conveyor of hidden water. Subduction is the belt that pulls it down. As the slab dips, pressure rises, temperatures climb, and those hydrous minerals begin to change. Serpentine, full of hydroxyl, holds on deeper than you'd think, then dehydrates as the slab warms. Lawsonite and chlorite break down at their thresholds too, shedding water in pulses that migrate upward into the overlying mantle wedge. That's the shallow chapter most people know. Water lowers the solidus, mantle melts, arc volcanoes are born. But the story keeps going below the arcs, where not all slab-bound water is released. Some of it keeps riding down past the brittle world into the ductile mantle. Here, the mineral cast changes. Olivine transforms at about 410 kilometers into wadsleyite, a phase that can incorporate hydroxyl into its structure. In that pressure window, the slab's remaining fluids find new homes. Not as free liquid, but as defects in the lattice of wadsleyite. Deeper still, between roughly 520 and 660 kilometers, ringwoodite becomes the favored host, and it too can store significant water. The slab is now a courier inside a sponge layer, the transition zone. But this is a one-way ride, only until the phases change again. At about 660 kilometers, ringwoodite breaks down into lower mantle minerals that don't accommodate water. Where that boundary is warm enough, or where slabs stall and heat up, hydroxyls are expelled. Suddenly, the surrounding rock has a lower melting point than the water-saturated assemblage that just crossed the line. The outcome isn't a river. It's a film of partial melt dispersed along grain boundaries. Dehydration melting at the base of the transition zone. Meanwhile, at the top of the transition zone, something similar can happen in reverse. Upwelling mantle, plumes or broader return flow, rises and cools. And as pressure drops across the 410, wadsleyite becomes olivine again, losing its capacity to hold water. That released water can again trigger tiny percentages of melt. In both places, a little melt changes a lot. Seismic waves slow down and attenuate more than expected. Electrical conductivity increases. These are the footprints we can detect from the surface. None of this moves on human timescales. The loop is measured in millions of years, but the mechanics are immediate at each boundary. Water moves with reactions. As hydrous minerals enter a field where they're unstable, they decompose and pass their water to whatever phase can carry it. In the transition zone, that's wadsleyite and ringwoodite. Above and below, it's partial melt, migrating a little, pooling where structures allow, then being scavenged into rising magmas or frozen into place as conditions change. So the deep water cycle isn't a tidy conveyor. It's a paced exchange, a series of handoffs. Ocean atmosphere water gets bound into oceanic lithosphere at the ridge, altered on the way to the trench, carried downward in slabs. Near arcs, some dehydrates and drives volcanism. The remainder dives into the transition zone, where it can be stored for geologic ages. Later, mantle upwellings tap those hydrous domains and return volatiles upward, where they eventually become gases at volcanoes, hydrothermal fluids in crust, and at the end of a very long loop, part of the surface reservoirs again. Why does this matter? Because water is a lever on rock. It lowers melting temperatures by hundreds of degrees. so melts can form where dry mantle would stay solid. It weakens minerals, enhancing deformation, so plates can bend and subduct instead of shattering. It changes electrical behavior, letting us see deeper with
Magnetotellurics. It changes how seismic waves lose energy, letting us hear the presence of fluids and melt as they attenuate. In short, water tunes the engine of plate tectonics. Picture that drop from the opening. Never a drop at depth, always a defect, an agent. Its path threads through phase transitions that act like valves. At 410, the valve opens to storage. At 660, it opens to release. Plumes and slabs control which way the pressure goes. When those valves align with a rising column of hot mantle, the stored charge can discharge, feeding magmas with extra volatiles, priming eruptions to be more explosive, and steering where volcanoes build their cones and calderas. If water controls where and when rock melts, it controls the difference between quiet and violent. And if it can be stored in the planet's middle layer for ages, the timing of its release isn't a weather forecast, it's geology's long fuse. The sponge layer, Earth's transition zone. Drop into the layer that does the quiet work. The transition zone is a band of mantle, roughly 410 to 660 kilometers down, where minerals switch identities under pressure. It isn't a flat shelf. It's a living boundary with chemistry that reacts to what the planet is doing above and below. In this window, the same basic ingredients, magnesium, silicon, oxygen, rearrange into phases that can hold water in ways the upper and lower mantle can't. At the top of this band, olivine transforms into wadsleyite. That sounds like a textbook name until you hear what it does. It takes hydrogen into its structure as hydroxyl defects. In that state, wadsleyite can store on the order of about 0.65 to 1.5 weight% water depending on temperature, oxygen conditions, and composition. Deeper in, wadsleyite transforms into ringwoodite, which also accepts hydrogen, and in experiments and that diamond inclusion can reach roughly 1 to 2% by weight. Not free water, no pore spaces filling up, just hydrogen and oxygen bound into crystal sites, invisible unless you know where to look. Scale matters. Spread even a fraction of a percent of water across a shell that thick and planet-wide, and you're talking the potential of an ocean's worth of hydrogen, unevenly distributed in stone. But this isn't a uniform sea. It's patchy, more like saturated soils and dry pockets in a mosaic. Some sections of the transition zone sit beneath subduction corridors, where slabs have spent millions of years delivering hydrous minerals downward. Others lie beneath stable cratons or away from slab influence, where the supply is weaker. The sponge image holds, but it's a sponge that's been squeezed and soaked unevenly. We can't drill there, so we infer its state from what waves and fields tell us. Seismic waves run slower in some parts of the transition zone, and they lose energy, attenuate, more strongly than a dry, uniform mantle would. That's a clue pointing toward elevated temperature, a touch of melt, or changes in grain boundary behavior caused by water. At the boundaries, the signals sharpen. Near 410 kilometers, where olivine becomes wadsleyite and the water capacity grows, upwelling material can exsolve water and create tiny films of melt. Near 660, where ringwoodite breaks into lower mantle phases that won't hold hydrogen, warm slabs or stagnant piles can expel stored water and again produce partial melts. Those thin melts aren't lakes, they're films along grains that are enough to change how waves travel. Electrical conductivity adds another line of evidence. Dry, crystalline mantle is stubbornly resistive. Add even a little melt or water in defects and the conductivity jumps. Magnetotelluric imaging, using natural electromagnetic variations, maps these jumps as conductive pathways. Under volcanic arcs and some plume-fed regions, MT surveys sketch ribbons and lenses of higher conductivity that match where seismology hints at fluids and melts. None of these techniques measure water directly. Each has ambiguity. Conductivity can also be elevated by graphite or sulfides. But when attenuation, velocity, and conductivity point to the same places, the case for hydrous, partially molten domains grows stronger. Mechanically, this band behaves like a buffer. It stores water in phases that can hold it, metering that water in and out across geologic time as pressures and temperatures change. It also acts like a valve. Wadsleyite and ringwoodite can accept hydrogen when slabs descend into their stability fields. They release it where upwelling or heating pushes materials across phase boundaries with lower water capacity. That's why the capacitor metaphor resonates. Subduction charges the layer slowly. Tectonic reorganizations and plumes can discharge it quickly, in geologic terms, by feeding volatile rich melts that rise more easily and erupt more violently.
Geographically, the pattern makes sense. Under Western Pacific subduction systems, deep seismicity and slab tomography suggest cold slabs ponding. And
warming around 660 kilometers. That's a setup for stored water being released at depth. Under mid-plate hotspots, seismic images sometimes show low-velocity conduits punching through the transition zone, with hints of a broader, hot base tapping that layer. In continental interiors, beneath old, thick cratons, the transition zone often looks more resistive and seismically faster, drier and cooler. That patchwork means the secret ocean is not a single reservoir. It's a set of connected, reactive storage zones. There's a catch we need to accept. The physics we use to see this layer all have non-uniqueness. Low velocity can mean hotter rock, grain size effects, or a bit of melt. High conductivity can come from melt, from certain minerals, or from hydrogen in defects. That's why the lab work matters. Mineral physics sets bounds on how much water these phases can hold at given pressures and temperatures. Those bounds keep the inferences honest. If a model implies more water than wadsleyite can store at 140 degrees Celsius, the model is wrong. So what is the transition zone? It's the memory foam of the mantle. It takes the imprint of plates and plumes, their chemistry and heat, and holds on to water until conditions force it to let go. When it does, melt appears where it otherwise wouldn't. Magmas carry more gas than they otherwise could, and the surface feels the difference. In arc chains that light up, in flood basalts that darken skies, in the slow rhythm of a planet breathing through stone. The fuse we talked about in the last act runs through here. This is the place that keeps time. Volcanoes that drink the deep. Arc volcanoes don't just sit above subduction zones by accident. They tap a plumbing system that starts with seawater on the seafloor and ends as steam in the sky. The surprise is how far that water can travel before it matters. Some is shed shallow, yes, but a meaningful fraction rides the slab down into the transition zone. When upwelling mantle or a rising plume intersects that hydrous storehouse, the result is magma that carries extra volatiles from birth. Watch how it changes the recipe. That's a volcano that drinks deep. Take dry peridotite and heat it. Nothing happens until it reaches a high solidus. Add water and the melting point drops by hundreds of degrees. Now small degrees of melt appear along grain boundaries, and those melts are enriched in water from the first drop. They rise because they're buoyant. And as they rise, pressure falls and more water comes out of the crystal structures into the melt, then into bubbles. That's where behavior shifts from gentle to violent. Gas-rich magmas fragment more readily. They don't ooze, they detonate. You can see the fingerprints in volcanic arcs around the Pacific. The Cascades, the Japanese arcs, the Andes, each chain owes its magma supply to water lowering the solidus in the mantle wedge. But the deep component shows up in how persistent and volatile rich some systems are. If transition zone domains beneath a given arc are well stocked, the melts feeding that arc arrive with more dissolved water. The eruptions tend to be more explosive, the gas plumes taller, the ash columns thicker. Not every eruption needs deep water, but when it's there, it tilts the odds. Hotspots complicate the picture. Many are fed by mantleplumes that rise from depths at or below the transition zone, punching through that sponge layer on their way up. If a plume's base spreads beneath 660 kilometers, it can warm and tap hydrous ringwoodite domains, scavenging water that's been stored for ages. Iceland is a case study in mixing. Plume heat meets a spreading ridge, while geophysical images suggest a conduit that intersects the transition zone. Hawaii, though basaltic and often effusive, carries variable volatile loads that hint at deep source heterogeneity. The message is subtle but steady. Plumes don't ignore the transition zone. They interact with it, even if the degree varies by case. On smaller, faster timescales, the effect shows up in magma ascent. Water dissolved in melt changes viscosity. It can keep magmas mobile at lower temperatures, moving through the crust rather than freezing. It also changes crystallization paths. Hydrous basalts evolve to andesites and dacites more readily, building magma reservoirs that are primed for explosive release. When monitoring networks catch rising gas ratios, swelling ground, and tremor, they're watching volatiles unbinding, water and CO2 leaving solution and inflating the system. The deeper the volatile budget, the longer such systems can cycle between recharge and eruption. We don't measure that deep budget directly. We infer it. Seismic attenuation beneath arcs points to small amounts of melt in the wedge.
MT surveys image conductive ribbons that trace possible fluid-rich pathways feeding arc routes. Petrology reads the glass and crystals ejected in eruptions, their water contents, their pressure-temperature histories. Every line
points back to the same quiet truth. Volcanoes are not just heat engines, they are chemical engines, and water is their throttle. This isn't just about bigger eruptions. Water in magmas changes how volcanoes build and collapse. It promotes hydrothermal systems that alter rock into weaker clays, setting the stage for sector collapses and lahars. It creates acid fluids that eat conduit walls, widening pathways and destabilizing domes. A deeply hydrated supply keeps those systems active between eruptions, humming with steam, earthquakes, and subtle ground motion. In the wrong place, a city on a flank, a reservoir downstream, that background activity is the hazard as much as the blast. There's a sobering long view too. Over tens of millions of years, arcs migrate, plumes wax and wane, slabs stall and steepen. Each reorganization changes which parts of the transition zone are tapped and when. Some intervals deliver steady, moderate, volatile flux. Others line up the valves, a hydrated transition zone, a hot upwelling, a thinning lithosphere. The discharge is not a single event, it's a cluster. Decades to centuries of elevated eruptive activity regionally, or the onset of a flood basalt if conditions are extreme. The timing isn't ours to choose, it's set by plate motions and mantle flow. What about the myth of an ocean bursting from below? That's not how this works. There's no free sea ready to surge. The catastrophe is different and real. Volatile charged magmas that can turn a clear morning into night, shut down air corridors, contaminate water, and load the stratosphere with aerosols. The deep reservoir's danger is indirect. It makes more melt in more places more often, and it hands those magmas the gas that makes them efficient at reaching the surface and disruptive when they do. Stand on a caldera rim and feel that steady exhale, the hot breath carrying a little more water every hour than the last. That's the deep cycle speaking. A volcano that drinks the transition zone doesn't roar all the time. It sips for decades, then gulps in a week. When it does, the plume tells you how far down its straw reaches. Plates, friction, and the grease. You can't see. Plates don't just collide. They grind, creep, and stall along contacts measured in hundreds of kilometers. What decides whether they lock hard or slip quietly comes down to what's in the tiny spaces between grains. Water, sometimes as true fluid in the crust, often as hydrogen in defects deeper down, changes that friction in ways you can't see from the surface, but you feel when the ground lets go. Follow a subducting slab beneath an arc. Near the trench, the downgoing plate drags pore fluids, sediments, and altered basalts into a zone where pressure compacts, heats, and squeezes water out. That water migrates up and along the plate interface, into the melange of sheared rocks and serpentinite that forms the plate boundary. Serpentinization is chemistry's softener, olivine, plus water makes serpentine, magnetite, and hydrogen, lowering rock strength and adding what amounts to geologic grease. A boundary with more serpentine behaves differently than one that's dry. Farther down dip, temperatures rise and those hydrated minerals decompose. Fluid is released again, but now it's at depths where brittle failure gives way to ductile flow. The middle ground between them, the transition from stick-slip earthquakes to slow, steady creep, is where water shows its hand. In subduction zones like Cascadia in southwest Japan, geodesy and seismic networks record episodic tremor and slip, weeks-long, slow earthquakes that relieve strain without the sharp shocks of a magnitude 7. Their migration patterns trace pressure pulses diffusing along the plate interface. The agent that carries those pulses is fluid. Seismic attenuation helps pick out the wet zones. Beneath the forearc, waves lose energy faster than expected. That elevated attenuation, along with lowered velocities, lines up with regions thought to be overpressured by fluids. It isn't the same as seeing water, but it's a footprint consistent with it. Tiny films along grain boundaries, overpressured pockets at the base of the crust, channels in a ductile shear zone. When those pockets connect, the effective normal stress on the fault drops. With less clamping, sliding can begin at lower shear stress, creep, tremor, or a cascade that runs out as a moderate quake. On continental faults, the chemistry is different, but the physics rhymes.
Deep fluids rise along fractures, altering feldspars and pyroxenes into clays like smectite and illite. Those clays are weak. A clay-rich fault gouge can host a seismic creep. A clay-poor one is more likely to lock until it doesn't. Changes in fluid pressure, seasonal recharge, injection, or natural pulses tied to deeper metamorphic reactions modulate frictional strength in real time. The system looks solid, but it breathes. Zoom out and you see a pattern, where plates are hydrated either by seawater at ridges and trenches or by deep source fluids along old suture zones. Deformation is distributed and often quieter. Where they're dry and cold, strain localizes until it snaps. Neither end member is safer. Quiet creep can load the lock patch next door. Locked stretches can go decades without a whisper, then rewrite a coastline in minutes. Water doesn't remove hazard, it shapes it. What about the mantle under the plates, the deeper engine? There, water is mostly in defects, not as free liquid, but its effect on viscosity is large. A few hundred parts per million of hydrogen in olivine can lower viscosity enough to alter how the asthenosphere flows. Softer mantle zones become channels guiding slab rollback and trench migration. Softer shear zones at the base of plates decouple crust from mantle, letting plates glide with less basal drag. Over millions of years, that changes where stress accumulates above. A hydrated asthenosphere is an invisible conveyor that shifts where mountains grow and basins sag. Electrical methods let us trace some of these pathways. Magnetotelluric transects across arcs and forearcs pick up conductive layers at the base of the crust and along the slab interface. Zones where fluids, melts, or hydrogen in defects boost conductivity above the background resistive mantle. Seismic studies add the attenuation map. Together they outline corridors where fluids likely migrate. They also expose a hard limit. Conductors don't tell you pressure. A wet, low-pressure system can be as conductive as a wet, critically overpressured one. The difference between the two is the difference between steady creep and locked instability. That's why geodesy and microseismicity matter. They add motion to the picture. You can see the human stakes in places like Cascadia. Offshore, a broad, gently dipping interface shows tremor that marches along in 3-week waves every 14 months. Onshore, metropolitan corridors sit on soft sediments that will amplify shaking when the locked part of the interface breaks. In between, a conductive forearc channel suggests fluids are moving now, not just in the past.
The deepwater cycle reminds you that the source of those fluids isn't only the shallow dehydration above the arc. It stretches down into the transition zone that feeds the wedge and modulates its strength. This is the grease you can't see. Water that changes the rules without announcing itself. It lowers friction where you'd want it to, until the patch that stayed dry decides to fail. It weakens rocks that would otherwise jam, redirecting stress into neighbors that weren't ready. It doesn't care about zoning or building codes. It follows gradients, reacts at thresholds, and keeps time on a clock longer than cities last. And yet, by listening for tremor, mapping conductivity, and tracking ground motion down to millimeters, we can watch the grease at work. We can't drain it. But we can learn where it pools, how it moves, and when a quiet slip is the sound of a bigger release preparing in silence. Iron, heat, and a planetary magnet with mood swings. Start at the center, where nothing we've said about water should matter, and yet it does. Earth's magnetic field is born in the liquid outer core, a shell of molten iron alloy convecting around a solid inner core. Motion of that conductive fluid, threaded by magnetic lines, sustains the geodynamo. It needs 3 things: heat to drive buoyant flow, rotation to twist it, and a conductor to carry current. None of that sounds like hydrogen in a crystal 500 kilometers up, but the core doesn't live in isolation. What happens in the mantle controls how fast the core cools, how it loses heat, and where. Heat leaves the core through the core, mantle boundary, like light through a stained glass window, unevenly. Above some patches, the lowermost mantle is hotter and sluggish. Above others, cooler and more efficient at wicking heat. That heterogeneity shapes core convection patterns. Over millions of years, it can strengthen or weaken parts of the geodynamo, shift the balance between stable and chaotic flow, and set the stage for the field's mood swings, excursions, and full reversals. Here's where the deep water cycle enters through the side door. Water in the mantle lowers viscosity. A hydrated asthenosphere is softer. It convects more readily. It organizes mantle flow differently. Water also lowers melting temperatures, changing how and where melt forms, which in turn modifies mantle composition and its ability to conduct heat. These are small levers, but over geologic time, they redistribute heat flow patterns at the base of the mantle.
A wetter, weaker mantle can alter the shape and vigor of upwellings and downwellings, steering where slabs pool and where hot plumes rise from the deep. Those structures, cold slab graveyards and hot superplumes, sit right on top of the core and act as thermal throttles. Geophysically, we see the fingerprints. Seismic tomography maps two great low shear velocity provinces in the lowermost mantle, hotter, possibly compositionally distinct piles beneath Africa and the Pacific. Slabs subducted for tens of millions of years appear to accumulate around their flanks. Above slab clusters, heat extraction from the core is likely enhanced. Above hot piles, it may be muted. Add water's effect on viscosity higher up, and you've changed the plumbing that feeds these contrasts. You haven't touched the core, but you've changed the boundary conditions, it feels. Does that steer reversals? The honest answer is, it might nudge, but it doesn't push the button. Field reversals are chaotic outcomes of a self-sustaining dynamo. They've happened with different supercontinent layouts, with different slab fluxes, under different atmospheric chemistries. There's no evidence a single water release event flips the field. What's more plausible is a long time-scale coupling. Mantle structure modulates heat flux heterogeneity at the core mantle boundary. That shifts the dynamo's operating state. Sometimes the field becomes unstable enough to reverse. Correlation is not causation, and the timescales are glacial compared to a human life. But the coupling is real. The mantle sets the stage, the core improvises. Why should anyone outside a geophysics lab care? Because the magnetic field is a shield. It deflects charged particles from the solar wind and coronal mass ejections. When the field weakens, during an excursion or on the lead up to a reversal, more radiation can reach near Earth space. Satellites and power grids become more vulnerable to geomagnetic storms. The atmosphere doesn't vanish, but the operational risks rise. Airlines reroute, astronauts shelter, high-latitude grids brace for induced currents. None of this is apocalyptic, but it's more than academic. Tie this back to the deepwatercycle and the ticking clock. Water's influence on mantle rheology and melting is a control knob on how heat moves upward. Imagine two Earths, one with a bone-dry asthenosphere, stiffer, shedding heat differently. One with a softly hydrated asthenosphere, more ductile, with different
plume lifetimes, different slab stagnation depths, different thermal maps at the base. The core under each Earth would operate under distinct boundary conditions. Over tens of millions of years, their magnetic histories would diverge. Not because water changes iron, but because it changes the mantle scaffolding that the core feels. We do have ways to listen to this coupling. Seismic attenuation tells us where the mantle is softer and hotter. Magnetotellurics traces where conductivity is elevated by melts or hydrogen in defects. Together with velocity models, they map the mantle's ability to move heat, its radiators and insulators. Mineral physics constrains how much water phases can hold, so we don't overfit conductive anomalies with impossible hydrogen budgets. None of these tools reach the core, but they sharpen the map of the boundary conditions we hand to the dynamo. There's a limit we need to hold. It's tempting to turn every deep water story into a field reversal prediction. Don't. The link is indirect and slow. The same goes for fear of a sudden magnetic collapse tied to a volcanic decade. Short-term volcanic or tectonic bursts don't steer the dynamo. What they do through aerosols and climate feedbacks is challenge the surface. The magnetic field's challenges are separate and paced by the deep interior's long memory. Mantlewater likely modulates boundary conditions rather than forcing outcomes. Still, the connection matters because it reminds us that Earth is one machine. Hydrogen bound in ringwoodite melt along a grain boundary, a slab flattening at 660 kilometers. These are not trivia. They are the settings on the dials that control heat flow, and heat flow feeds the magnet in the dark. To see the stakes, though, we don't need to wait for a reversal. We need to watch what happens when deep water finds a fast route to the surface. When the valves line up, the discharge is not magnetic, it's volcanic. And when it's big, the sky tells the story. When rock boils, steam quakes in sudden lakes. When deep water finally joins heat on the way up, the rules flip fast. Magma doesn't need a lake to turn explosive, it just needs water to meet it, even as vapor or as hydroxyl leaving solution. As pressure drops in a rising melt, dissolved water exsolves into bubbles. Bubbles expand, link, and rip the melt apart. That shift, from liquid to foam to fragments, happens in seconds. Phreatomagmatic is the word, but the experience is simpler. Rock becomes steam-driven shrapnel. You see it in marked craters and tuff rings, those low rims around broad, flat-floored pits scattered through volcanic fields. In Auckland's monogenetic field,
Dozens of Mars record blasts where magma intersected groundwater. The magma doesn't have to be voluminous. What matters is the contact. Water flashing to steam expands by orders of magnitude, fragmenting melt and country rock, digging a crater that later fills with a lake. From the rim, it looks peaceful. In the moment, it's a pressure cooker that lost its lid. Yokolops tell a colder version of the same story. Beneath glaciers, ice-capped volcanoes melt hidden reservoirs against the bedrock. When a subglacial lake overtops a threshold or a meltwater tunnel opens, the drainage is sudden, hours to days. A valley that was a braided stream at breakfast can be a churning wall of water by noon, hauling boulders, grinding bridges. The eruption might be minor. The outburst flood is not. Water stores energy in silence. Release is the hazard. Hydrothermal systems do this on a small but deadly scale. Geyser basins and caldera domes are networks of fractures filled with near-boiling fluids under pressure. Seal a pocket with silica or clay, add heat from below, and the pressure climbs. A slip on a tiny fault, a drop in confining load after a quake, a clogged vent, and the seal fails. Steam flashes, volume explodes, and a shallow explosion crater scars the ground. No magma required. Afterward, the plumbing reconfigures, new vents open, and the clock starts again. What controls the odds is water content and pressure. The more water a magma carries, either from deep provenance or shallow assimilation, the earlier bubbles form as it ascends. Early bubble growth means faster acceleration and more fragmentation before gases can escape. That's why similar volumes of magma can behave so differently. One dome extrudes and pants for months. Another dome seals, overpressurizes, and shatters in a surge of ash and blocks. The difference is often water and how it moves between phases. Monitoring helps, but it's a race against hidden processes. Gas ratios at vents, H2O, CO2, SO2, shift as magma rises and degasses, giving hints about depth and saturation. Temperatures at hot springs creep upward. Chloride and silica concentrations change as reservoirs flush. Ground deformation swells and subsides as pressure cycles in the system. Microseismicity ticks like a Geiger counter when bubbles nucleate and pathways open. None
of these predicts on their own. Together, they sketch a system walking toward a threshold. Lead time can be days for hydrothermal failures, months for magma-driven events, if instruments are there and the signals are read with caution. Here's a micro-story that researchers tell in quiet tones. A field team was mapping altered ground on the flank of a restless caldera. They paused at a steaming terrace as the wind dropped, and the ground made a sound, like a giant sleeping animal, slow, deep breaths. That was the cap rock flexing over a pressurized pocket. They backed away. 2 days later, a hydrothermal explosion tore a crater the size of a house through that spot, hurled mud and rock 100 meters, and coated the surrounding pines. No warning siren, just pressure finally exceeding strength. Not every dramatic change needs an eruption. When rising magma or hot fluids intersect an aquifer, you can get sudden crater lakes where none existed, then equally sudden draining when a throat opens to a deeper level. The shoreline stains tell the story. A bathtub ring of iron and silica drop meters in a night. On maps, these are shrugged off as ephemeral. If you're downstream, they are anything but. The chain reaction is physics with an attitude. Water holds an enormous latent heat of vaporization. When it flashes, it soaks up heat and expands, driving fragmentation that exposes more hot surface, which accelerates flashing. A feedback that builds in a heartbeat. In confined spaces, that feedback fails only when the cavity has vented or the pressure source has been cut. In open systems, it paints the air with ash, shards of glass, and droplets quenched into fine particles that ride winds for hours. It's tempting to assign these scenes to the shallow world and leave the transition zone out of it. Don't. The deep water cycle sets the baseline water budget in magmas rising beneath volcanic provinces. A system fed by hydrous mantle sources will produce magmas that reach saturation sooner, build larger hydrothermal systems, and maintain pressurized reservoirs longer between eruptions. That means more Mars in a field, more restless caldera domes, more outburst floods under ice. The surface hazard is the local expression of a deep supply. Dramatic bursts make headlines. The slow part, the silent charging of reservoirs by a drip of deep-sourced water, is what makes those bursts likely. Our job, if we live near these systems, is simple and hard. Pay for the sensors, read the signals, respect the breath you can hear under your feet. Climate,
carbon, and the breath of a planet. When deep water rides a melt to the surface, it doesn't stop being a climate story just because it never made a river. It becomes cloud, it becomes aerosol, it becomes chemistry that lingers in sky and ocean long after the ash settles. Water, carbon dioxide, and sulfur leave the mantle as a package deal, and the balance between them decides whether a year feels cooler, a decade feels stranger, or a century bends its carbon curve. Volcanoes speak in short sentences and long paragraphs. The short ones are eruptions like Pinatubo in 1991, fast injections of sulfur dioxide into the stratosphere, where sunlight-forging chemistry turns it into sulfate aerosols. Those tiny droplets scatter incoming light, and for a year or two, the planet's fever dips by fractions of a degree. It isn't permanent climate repair, it's a temporary visor. The water in the plume is along for the ride, but sulfur does the cooling work by making the mirror. When the droplets fall out, the visor lifts, and the background warming resumes. The long paragraphs are about inventories. A mantle that's hydrated and actively melting more often feeds more volcanoes with more gas. Water lowers the melting point, so partial melts are easier to make, and every additional melt episode is a chance to move volatiles upward. Carbon that was stored in the mantle as carbonate or dissolved in melt becomes CO2 in the air. Sulfur becomes sulfate. Water is everywhere. None of it writes climate by itself, but together they nudge the balance. After a big eruption, you can watch the atmosphere learning a new mix. Flights that normally slice polar routes take longer, lower tracks to dodge radiation and ash. Sunsets go hyper-real as sulfate haze spreads. The troposphere, the weather layer, barely holds a memory. The stratosphere, above the storms, keeps one. 2 or 3 years of slight cooling is the common headline. The deeper lesson is the lever. A few tens of teragrams of sulfur, lofted high, can shift the planet's radiative budget. The ocean notices too. Ash and acid rain carry nutrients that can trigger short-lived blooms. Those blooms fix carbon, then sink. The effect is patchy, but real, a pulse in the ocean's slow carbon pump. Stretch the timeline to geologic and you see pacing. When the mantle's water budget is high in a region, because subduction has fed the transition zone and upwellings are tapping.
Eruption frequency and volatile throughput rise. Not every year, not every millennium, but over millions of years, arcs and hotspots with ready access to hydrous source domains deliver more gas. That changes how the long carbon cycle balances volcanic outgassing against silicate weathering. More CO2 raises temperatures, which speeds weathering, which draws CO2 down, a thermostat with lag built in. Water is in both halves of that loop. It makes the melts that vent CO2, and it rains on fresh basalt, driving weathering that consumes it. There's a persistent fear that the secret ocean could suddenly surface and drown coastlines. The physics won't let it. This reservoir isn't a lake under a lid. It's hydrogen tucked into lattice sites, liberated only as melt or vapor along narrow pathways. Surface sea level on human timescales is controlled by ice and thermal expansion, not a valve at 660 kilometers. The catastrophic pathways that are real build through gas, not flood. Think aviation corridors closed for weeks beneath an umbrella of ash. Think reservoirs spiked with sulfate and chloride in a day. Think crop seasons shortened by a dimmer sky. Still, the deep water lever matters because it changes how often and how forcefully those gas pulses happen. A wetter source means more hydrous melts, which means more eruptions reach volatile saturation and breach the surface, which means more chances for sulfate veils and CO2 boosts. The atmosphere integrates all of it. So do we, in power grids that arc under geomagnetic storms, while volcanic aerosols shift ionospheric conditions, in water systems that must switch intakes when ash clogs one basin, in air routes that become a game of chess when the stratosphere goes hazy. The ocean keeps its own books. Fresh basalt from increased volcanism draws down CO2 through weathering, but warmer waters hold less gas and change stratification. Iron and ash can fertilize, but not everywhere and not forever. The net effect is a tug-of-war with rules that depend on where the ash falls, how big the plume is, and whether the ocean is ready to use the gift. Deep water, by controlling how frequently magmas are born and how gas-rich they are, loads the dice for these bouts. None of this reads like a countdown clock until you realize how quietly the reservoir charges. Subduction feeds it with every cold slab that bends. Plumes and plate reorganizations decide when to spend it. The ticking is not a flood alarm. It's the cadence of volatile exchange between stone and sky.
If the deep ocean won't rise to our doorsteps, what exactly is counting down? The answer is local and lived. The intervals between volatile, rich eruptions in the places we built our lives. That's the clock worth hearing.
The ticking clock. Charge, pause, discharge. Think of the transition zone like a bank account with strange rules. Subduction pays in, slowly, relentlessly, by hauling hydrated minerals down and parking hydrogen in wadsleyite and ringwoodite. Upwellings make withdrawals, sometimes for ages, sometimes in bursts, by crossing phase boundaries that force water out and generate melt. Charge, pause, discharge. The clock isn't loud, but it's steady. On charging, slabs don't deliver a flood, they deliver a trickle that never stops. Serpentinized mantle and hydrated crust cross into the 410 to 660 kilometer window and hand water to the crystal lattice. That storage is patchy, but over tens of millions of years the balance grows. Where multiple slab tracks overlap, Western Pacific corridors, long-lived subduction systems, the account grows faster. Where slabs are scarce or old cratons sit above, it grows slower. The meter never hits full. Capacity depends on temperature, composition, and oxygen fugacity, but it climbs, on pausing. Most of the time, stored water just sits, changing the rheology of a layer we can't touch. The pause is geologically busy, but outwardly quiet. The transition zone is softer where it's wetter. Softer zones redirect mantle flow, detour slabs at 660, and help plumes find paths of least resistance. Meanwhile, the storehouse keeps accepting deposits. Seismology hears the pause as broad swaths of modestly lower velocities and higher attenuation. Magnetotellurics sees it as deeper than expected conductivity. Not everywhere, not uniform, just enough to suggest a wet buffer. It's not a still pond, it's a vault in a moving machine. Discharge starts when valves align. A plume head spreads at the base of 660 and warms hydrous ringwoodite. A ponded slab heats enough to cross a boundary that won't hold hydrogen. Upwelling across 410 strips wadsleyite of its water capacity. Each of those transitions creates films of melt that percolate, connect, and feed larger melt zones. You don't need much. Percent level melt can transform a mantle column's behavior. The payout doesn't have to be singular. It can arrive as a cluster, decades to centuries of elevated volcanism along an arc sector, a prolonged episode of volatile, rich hotspot activity. In rare cases, the conditions that precede a large igneous province. Timescales are the hard truth. The charge is tens to hundreds of millions of years. The pause is most of that. The discharge, a regional uptick, a sequence of arc paroxysms, can compress into human lifetimes. We won't hear the ticking until we feel the payout, but we can estimate the balance and watch the valves. That's where mapping the charge comes in. Seismic tomography outlines cool slabs that likely carried water into the transition zone. Warmer anomalies below 660 hint where release becomes possible. Seismic attenuation flags where the mantle is softer, hotter, or subtly melted. Conditions water helps create. Magnetotellurics images conductivity in the deep wedge and under arcs, consistent with hydrous melts or hydrogen-enhanced conduction in defects. Diamonds deliver ground truth in pieces. Inclusions that confirm ringwoodite and wadsleyite can be hydrous at depth. None of these tools measures water directly, and every one is non-unique. Higher conductivity could be melt, sulfides, graphite films, or hydrogen in defects. Lower velocity could be hotter rock, smaller grains, or fluids. That's why the picture is always qualified, a mosaic of probabilities bounded by mineral physics. Even so, the mosaic has patterns we can use. Where subduction is long-lived and fast, where slabs flatten at 660, where hotspots pierce the transition zone, the odds of a loaded capacitor rise. Where arc routes are both conductive and attenuating over broad swaths, the odds of an elevated volatile budget rise. Monitoring those places isn't speculative, it's triage. You prioritize corridors where the system looks primed to spend. What nobody knew for most of the 20th century is that we could even sketch this account. Now we can, roughly. We can say this sector of the transition zone is likely wetter, this one likely drier, this arc likely has a deeper volatile subsidy, this plume likely interacts with the 660-kilometer valve. We can't time a discharge like a storm front, but we can identify provinces where the reservoir has been charged and where geometry invites release. The moonshot is motion,
catching water moving between phases in real time. That means denser arrays along arcs, long-period seismic stations that can hear attenuation changes, magnetotelluric lines revisited to see conductivity drift, and laboratory work that ties small changes in melt fraction or hydrogen content to measurable geophysical shifts. It also means humility. These signals are subtle. The non-uniqueness won't go away, but every constraint shrinks the space of stories we tell ourselves about risk. The clock isn't a countdown to a mythical flood. It's a clock isn't a countdown to a mythical flood. It's a
cadence at depth that modulates how often volatile-rich melts appear and how likely they are to reach us. Charge, pause, discharge. Our window is the pause. That's when mapping matters, when cities can move plans from someday to ready, when a quiet mantle is the time to listen hardest. Listening to the planet's plumbing. If you want to know where the deep water is moving, you don't look for lakes. You listen for changes in how the planet carries current and sound. The toolkit is quiet but ruthless. Magnetotellurics, or MT, borrows energy from the sky, auroras, solar wind, global lightning, and waits. Those natural electromagnetic waves roll over the planet, and tiny fractions diffuse into the ground. Dry, crystalline mantle resists. Add a trace of melt or hydrogen bound in crystal defects, and conductivity ticks up. Lay out electrodes and magnetometers, record at many frequencies, and the depth comes for free. High frequencies hear shallow, low frequencies hear deep. Stack hundreds of stations across an arc, invert the data in 3 dimensions, and conductive ribbons appear where melts and fluids find paths. Seismology gives a second independent map. Velocity shows how fast waves move. Attenuation shows how much energy they lose. Hotter, softer, slightly melted mantle makes waves tire quickly. That loss, quantified as low Q, clusters beneath 4 arcs, along slab tops, and at the 410 and 660 kilometer boundaries where water enters and leaves crystal structures. Receiver functions add the edges, sharp jumps where phase changes stack up. Together, they outline the valves we've been talking about. Not as a guess, but as a pattern you can trace from Japan to Cascadia to the Andes. Diamonds, improbably, are the field samples from places we can't reach. Inclusions locked inside, spinel, bridgemanite precursors, hydrous ringwoodite, carry the pressure, temperature, and chemistry of the depth where they formed. When a blue speck of ringwoodite inside a Brazilian diamond revealed hydroxyl in its lattice, it turned a suspicion into a measurement. The transition zone can be wet. Each inclusion is a postcard from a depth we otherwise only model. Offshore, we push the same listening out past the shelf. Ocean bottom seismometers hear plume conduits punching upward beneath hotspots. Marine MT adds conductivity beneath salt and basalt, where seismic alone struggles. Seawater screens high frequencies, so marine MT leans on longer periods, hours to days, to see beneath the conductive ocean. It's slower work, but the reward is a view under some of the most active margins on Earth, where slabs dive and volatile budgets are set. Then there's the lab, where we grow mantle minerals under the right pressure and temperature and force water into their structures. Wadsleyite and ringwoodite samples tell us how much hydrogen they'll accept at given conditions, how that changes conductivity, and how even a percent level melt lights up an MT model. Those calibrations keep the field honest. If an inversion implies conductivity that would require impossible water contents, the inversion is wrong. Mineral physics is the ruler we hold against the shadows. We're also getting better at spotting motion. AI combs through continuous seismic records to find swarms of tiny quakes and tremor, signatures of fluids migrating along faults and through ductile shear zones. In some arcs, those tremor trains sweep along the slab top like a pressure wave, right where MT images a conductive channel. Gas sensors at the surface watch H2O, CO2, and SO2 ratios shift, tracking magma ascent and degassing depth. Satellite interferometry measures ground swelling down to centimeters, mapping reservoirs inflating and deflating on timescales we live on. None of these is definitive alone. Together, they turn a static picture into a living one. Early warnings aren't magical, they're layered. In hydrothermal systems, a slow climb in temperature,
A subtle uptick in chloride and a pocket of seismic noise can precede a steam-driven blast by days. In magma-driven unrest, gas ratios change first, then deformation, then a chorus of high-frequency quakes as cracks open. Add an MT repeat line, and you might catch a conductive zone expanding as melt or hot brine connects new pathways. It's not fortune-telling. It's plumbing diagnosis. There's a human cadence to the work. A crew hauls non-polarizing electrodes across a pumice plain and buries them shallow to avoid frozen ground. Induction coils go in trenches, aligned north, south, and east-west, quieted from wind. Weeks later, the time series come home. Tiny voltages and magnetic wiggles transformed by Fourier analysis into apparent resistivities and phases. The first plots look like noise. The inversion sharpens into structure. A resistive block, old, cold crust. A conductive sheet along the slab, fluids and clay-rich melange. A deeper lens beneath the arc, melt fed from a valve at 410. None of it is water on a map, but each piece is a
testable story. We also confront limits. MT can tell you a layer is conductive, but not whether the pore pressure is near failure. Seismic attenuation can tell you rock is soft, but not whether today's tremor is headed for rupture. Non-uniqueness isn't a flaw. It's the price of sensing a planet with passive signals. The way around it is synthesis, multiple methods, repeated over time, tied back to lab bench physics. And that brings us to the scale that rewrites maps. The same valves that feed arcs can, under rare alignments, open a fire hose. Not a flood of liquid, but a flood of melt and gas sustained long enough to change air, ocean, and life. The record has a name for those intervals. Now we turn to it. Flood basalts. When the planet opens the fire hose, there are eruptions that make headlines, and then there are events that redraw the ledger of life. Flood basalts belong to the second kind. They don't build combs, they drown provinces. For months to millennia, fissures split and stay open, feeding curtains of lava that pour across landscapes in sheets tens of meters thick. Stack those sheets, eruption after eruption, and you bury continents under kilometers of basalt. It's not spectacle, it's a regime change. Start with what they are. Continental flood basalts and oceanic plateaus are the planet's largest volcanic outpourings. The Deccan in India, the Siberian traps in Russia, the Columbia River basalt group in North America, the Ontong Java Plateau in the Pacific. Each represents a brief geologic pulse where magma generation and delivery outpace the crust's ability to cool and cap it. The result is volume on a scale that defies ordinary experience. Millions of cubic kilometers in a geologic blink. Volatiles are the multipliers. Basalt seems simple: iron, magnesium, calcium. But the story turns on its dissolved gases. Water and CO2 do two things that matter. First, in the mantle source, water lowers the solidus, so more melt is produced for the same thermal input. Second, in the crust, those melts rise already primed with gas. As pressure drops, volatiles exsolve, driving buoyancy and keeping the system open. On flood basalt timescales, that means less choking, fewer pauses, more sustained supply. Sulfur rides along as well, injected high into the atmosphere by giant fire fountains and convective columns over fissures. It builds sulfate hazes that dim sunlight. Climate doesn't wobble, it lurches. The case studies read like cautionary epics. Around 252 million years ago, the Siberian traps erupted for hundreds of thousands of years near the Permian-Triassic boundary. The timing matches the greatest mass extinction on record. The mechanisms stack. Sulfur aerosols caused short cold snaps. CO2 and halogens drove long warming and ozone stress. Basalt baked carbon-rich sediments spiking methane. Acid rain stripped soils. Oceans lost oxygen, reefs collapsed, forests died back. It wasn't one explosion. It was a sustained atmospheric and oceanic assault. The Deccan traps, about 66 million years ago, overlap with the end Cretaceous extinction. Chicxulub gets the headlines, and it should. A bolide impact is a singular blow. But the Deccan eruptions bracket that event and likely worsened the recovery. CO2 from Deccan lavas warmed climate on million-year scales. Sulfates and ash produced short-term cooling. Acid aerosols stressed ecosystems already on the edge. Two hammers, different tempos, same anvil. The kill mechanisms are messy but coherent. Volatilized gases shift climate and chemistry faster than many food webs can adapt. Where does the deep water cycle enter? In the source.
One pathway to the volumes involved is a hot mantle plume head impinging on lithosphere and spreading, generating decompression melting across a broad area. If that plume crosses or ponds at the base of the transition zone, it can tap hydrous ringwoodite domains. A wetter source yields higher degrees of melting at a given temperature and may keep conduits open longer. It doesn't prove that every flood basalt drinks the transition zone. It sets a plausible stage where deep stored hydrogen becomes a silent partner in the outpouring. Geophysics offers hints rather than verdicts. Some plume-fed regions show seismic low-velocity conduits punching through the 410 to 660 kilometer window, with possible pooling at 660 before ascent. Electrical conductivity beneath certain provinces is higher than expected for dry mantle, consistent with hydrogen and defects or small melt fractions. None of this is a smoking gun. The data are non-unique. But multiple streams, seismic velocity, attenuation, conductivity, geochemistry, converge on a narrative where plumes interact with a hydrated transition zone. The degree of that interaction likely varies by case. What makes flood basalts particularly effective at changing climate is pacing and plumbing. They don't just vent from a single point. They erupt from distributed fissures and dike swarms that can extend hundreds of
monomiddles. That geometry couples magma to atmosphere efficiently. Fire fountains loft gas, lava flows roast sediments. Volatile throughput is continuous enough to keep background levels elevated between pulses. In that environment, weather becomes a memory and climate the driver. Acid rain leaches soils, greenhouse spikes warm oceans, oxygen declines choke marine life, and recovery is a long walk back. Clarify the uncertainty. Not every mass extinction lines up with a flood basalt, and not every flood basalt is catastrophic. Paleogeography matters. Where the lavas erupt, what sediments they intrude, how the oceans circulate, impacts can tip a system already sliding. Continents can be positioned to amplify or dampen feedbacks. Deep water is one lever among several. It doesn't fire the system alone, it primes it. So why fold this into a story about a secret ocean? Because the same valves that meter water into arc magmas and hydrothermal systems can, under rare geometry, scale up. A hydrous mantle source is more meltable. A plume that lingers at 660 can mine that meltability and volatile supply. The fire hose opens not as a jet of liquid water, but as a sustained, gas-rich melt production that holds fissures open and loads the sky. Flood basalts are the extreme expression of a planet whose middle layer stores and spends. Bring it back to now. We don't live under a province about to drown in basalt. The risks we face are smaller scale and nearer term. Volatile, rich eruptions and arc chains beside megacities. Aerosol veils that snarl aviation and nudge seasonal climate. Water systems and grids tested by ash and acid rain. The fire hose is a lesson in mechanism, not a forecast. It shows what happens when the valves align and stay open. Our job is to read the plumbing before it does. The modern fault lines, where deep water touches our lives. Stand on a coastal bluff above Tokyo Bay and trace an invisible line offshore. Beneath that water, the Pacific Plate slides under Japan, carrying fluids in its pores and minerals that once drank the ocean. Those fluids don't announce themselves, but they change how this boundary breathes. Weeks of tremor roll along the slab top like a whispering storm. Then silence. Then another wave. The city hums on, but the fault is talking in water's language. Jakarta sits over a different geometry, where the Indo-Australian plate dives beneath Sumatra and Java. Here, deep fluids do two jobs at once. They soften the four-arc melange, encouraging slow slip that relieves strain quietly. They also feed a line of volcanoes, Merapi, Semeru, that live by the volatile budget of the wedge. A wetter wedge is a more restless wedge. On the coastal plain, that means ash over airports, lahars and riverbeds, and a sky that can go from clear to clotted in hours. Mexico City's hazard is layered. The Cocos Plate hydrates the mantle beneath the trans-Mexican volcanic belt, where Popocatépetl exhales daily. Beneath the city, ancient lake clays magnify waves. The deepwatercycle doesn't move the buildings. It primes the magma, feeding a volatile, rich conduit, and modulates how and when the subduction interface slips. When it does, shaking is worse on the wet, compressible ground the city is built on. Deep water sets the tempo. Shallow water sets the acoustics. Naples frames the same physics in a tighter box. Campi Flegrei is a caldera plugged by altered rock and laced with hydrothermal veins. Its magma has a history with water.
volatile, rich, prone to overpressure. The ground swells and sinks, bradyseism, over years as gas and hot brine shift in the crust. Gas ratios tilt, CO2 rises, steam vents intensify. None of that requires magma ascent. All of it requires water in the system. The deep reservoir helps load the dice for a densely populated rim. Cascadia is the quiet giant. Offshore, the Juan de Fuca plate is young, hydrated, and warm. Onshore, geodesy tracks a slow, seasonal breathing as snow loads and groundwater masses change, superimposed on a deeper rhythm. Episodic tremor and slip pulsing every 12 to 18 months along the slab interface. MT transects across the forearc reveal a conductive channel at the slab top, consistent with fluids and clay-rich melange. Seismic attenuation maps a softer zone beneath the arc, where melt and water lower Q. Together, the picture isn't a countdown. It's a system near multiple thresholds, some creeping, some locked. Volcanoes under watch draw from the same plumbing. Fuji has slept for centuries, but its volatile budget hasn't vanished. Popocatépetl cycles ash and gas with a steadiness that belies the deep flux. Campi Flegre's hydrothermal lid presses on a volatile charged interior. Aeso in Kyushu sits where multiple slabs thread the mantle, feeding a long-lived, water-rich system. In each case, water content shifts where crystallization starts, how viscosity evolves, and when bubbles take over. A modest injection can flip behavior from effusive to explosive. Infrastructure feels every choice the subsurface makes. Ash and jet engines melts, coats turbine blades, and quenches flight paths in minutes. Sulfate-rich rain corrodes transformers. Acidic fallout spikes surface water. Utilities scramble to reroute intakes and adjust treatment. When aerosols load the stratosphere, satellite links and ionospheric conditions wobble, nudging power grids at high latitudes. None of this is a mythic deluge. It's a cascade of manageable failures if you expect them. Adaptation is logistics backed by physics. Along arcs, dense arrays of broadband and long-period seismometers listen for tremor and attenuation changes. MT lines on land and offshore track conductive corridors that can evolve as melt connects or brine shift. Continuous gas sensors watch H2O, CO2, SO2 ratios. Sudden swings flag the gassing depth changes. GNSS networks and INSAR map millimeter scale swelling. In geothermal fields and caldera basins, temperature strings, chemistry sampling, and pressure transducers turn hydrothermal systems into monitored pressure cookers with gauges. The point isn't to predict to the hour, it's to buy lead time. In a hydrothermal field, a week's warning moves tourists off a trail and workers out of a crater. In an urban arc, months of elevated gas and deformation trigger ashfall plans. Stockpiles of filters, water bypass protocols, rerouted power, alternate runways. In subduction zones, tremor campaigns paired with offshore MT and ocean bottom seismometers refine where the interface is fluid-rich and decoupled versus locked and primed. That map informs building codes and retrofits more rationally than a line on a hazard map drawn in the 198s. There's humility built in. Conductors on an MT map don't tell you pressure. Low Q beneath an arc doesn't say when a vent will open.
Non-uniqueness forces us to triangulate. Conductivity, velocity, attenuation, gas, deformation, chemistry, all bounded by lab constraints on how much water minerals can hold and how little melt it takes to light up a model. The payoff is probabilistic, not prophetic. Then there's the human layer. A technician in the Andes digs a trench for induction coils while lightning cracks over the altiplano. A student in Hokkaido watches a tremor front crawl across her screen at 5 kilometers per hour. A hydrologist in New Zealand samples a crater lake in a respirator as chloride jumps overnight. None of them can see the hydrogen bound in Ringwoodite 500 kilometers down, but they live by its schedule. The deepwatercycle isn't an abstraction. It's the hidden context for the choices cities make on the surface, whether to bury cables, to diversify water intakes, to practice an evacuation route before the sky goes gray. If there's a lesson, it's this. Where deep water touches our lives, the hazard is multiplied by surprise. The physics is slow and the failures are fast. Our job is to slow the failures down, to turn bursts into warnings, panic into protocol, by listening to the planet's plumbing and acting before it boils. The plan? From surprise to lead time. We've mapped the plumbing. Now we have to use it. The goal isn't prophecy. It's time. Time to close a trail before a hydrothermal blast.
Time to reroute flights before ash meets turbine blades. Time to spin up water treatment before an acid pulse hits a reservoir. Lead time is built, not granted. Start where the risk concentrates. Subduction arcs and Caldera systems. Build dense, layered sensor webs along those corridors, onshore and offshore. On land, run broadband and long-period seismometers for velocity and attenuation, GNSS for slow deformation, continuous gas stations for H2O, CO2, and SO2 ratios, and repeat magnetotelluric profiles for conductivity drift as melt connects or brines shift. At sea, add ocean bottom seismometers, pressure sensors, and long-period marine MT to image slab-top fluids and deep wedge conductors through the conductive blanket of seawater. Treat each arc like a weather front, watched continuously, not visited once a decade. Make the data live together. Open data isn't a slogan, it's plumbing syntax. Cross-link seismology, MT, INSAR, GNSS, gas, groundwater chemistry, and temperature strings in hydrothermal fields. Let machine learning crawl continuous records for patterns humans miss. Migrating tremor fronts that announce fluid diffusion. Subtle phase shifts in MT that hint at new connectivity. Microquakes that cluster where a brittle lid is thinning. The AI doesn't replace a geologist. It hands one a short list before breakfast. Tie the field to the bench. Mineral physics is the yardstick that keeps maps honest. Keep refining how wadsleyite and ringwoodite store water at given pressure, temperature, and oxygen fugacity, and how hydrogen in defects or percent level melts shift conductivity and attenuation. Feed those calibrations into inversions, so conductors don't become impossible oceans and soft zones, don't imply melts that mineral physics forbids. Wherever possible, anchor the models with petrologic constraints from erupted glasses and crystals, real volatile contents and pressure temperature paths. Plan for the boring failures. Hydrothermal systems are pressure cookers with clogged vents. Treat them that way. Install pressure and temperature arrays, chemistry sampling, and acoustic sensors around geyser basins and caldera floors. Write trigger protocols. A certain rise in chloride and temperature, plus a gas flux jump closes boardwalks, reroutes tourists, and increases patrols. In cities near arcs, stockpile N95 equivalent filters for ash, swappable water intakes, and mobile transformers hardened against acid deposition. Build power and water reroute playbooks and practice them. Invest like it's weather. Funding follows storms because the forecast pays off in saved lives and dollars. Volcanic and subduction hazards deserve the same logic. Budget for sustained monitoring, not just post-eruption grants. Fund repeat MT transects, not just single snapshots. Time is the whole point. Expand offshore arrays where arcs meet megacities. The slab top sets the tempo for both tremor and volatile budgets. Build regional data centers staffed to fuse signals and issue risk updates with confidence and humility. Bring people in. Where communities trust the instruments and the people behind them, warnings are heeded. Publish dashboards with gas ratios, deformation rates, tremor maps, and MT-derived conductor changes explained in human terms. Train journalists before crises. Run drills that begin with, "We don't know if this will escalate," and end with buses rerouted and shelters opened. The plan doesn't remove uncertainty, it manages it on purpose. Here's the human story that matters. A scientist notices a tremor band migrating along a conductive slab top.
Channel her team mapped with MT last year. Gas ratios at the nearest volcano quietly tilt toward deeper degassing. GNSS shows a 1 centimeter swell on the edifice over 10 days. None of it triggers a siren. But taken together, the lab thresholds say the system is inflating. 48 hours later, with air filters staged, intake shifted, and flights repositioned, an ash column punches into the sky. It's disruptive, but it isn't a surprise. That difference is the plan. We started with a mythic flood. The real one we can prevent is made of missed hours. The fix is patient. Listen constantly, fuse signals, act early. Lead time is the only currency that spends well against stone, and it's built from the quiet physics of hydration, melting, and signals we can measure. What the planet is whispering. The Mantle's secret ocean isn't a wave waiting to rise. It's a reservoir that sets the tempo of fire and breathes through stone. If you want the next warning, don't look for water. Listen for motion. If this kept you watching, share it with the one friend who loves big, weird Earth secrets. Subscribe for more true stories told with the science intact, and watch our next episode to see how one quiet tremor unlocked a city's evacuation plan.